Okay, we're not done yet. The last question says to plot the signal V1 and Vs. So what I recommend for this question is you use your graphing calculator to punch these time domain expressions into your calculator and try to get it. Okay, but the first thing is we need to adjust this expression first. So what do I mean? Okay, so we're gonna change everything that we see in degrees into radians. I'll explain why later. So this 71.6 is in degrees, right? Let's change it to radian. So how to change it to radian? Divided by 180, multiplied by pi. Okay, so this phase will be converted to radians. This phase is 0, which is just 0 even in radians. Yeah, so now we can chop this into our calculator. The reason why I changed this phase into radians is because this 2 pi is your radian frequency. And what's the radian frequency in? The radian frequency is in radians. So you need to have your phase also in radians to keep the consistency. You can keep it in different units, provided you explicitly say, okay, this is in degrees. This one is implied in radians. Okay? You're never gonna have degree per second. It's rarely the case. It's never the case, in fact. Okay, so when you put it in your calculator, you need to change this phase into radians. So let me demonstrate how to put this into your calculator. Okay, so I have my calculator out. Now I shall punch in V1. So V1 is given by, and this is my phase, 71.6 divided by 180 multiplied by pi. Now notice that I put x instead of t because my calculator has its horizontal axis in x, so it doesn't matter. Just follow suit. So you make sure that your calculator is also in radians, okay, not in degrees, and you enter this. You should get a sinusoidal wave. Okay, I'm gonna do the next wave. Okay, wait, let me just zoom out of this. Is so frustrating. Okay, zoom out. Hold on. I need to close this. Sorry. Let me restart. So my graphing calculator does something wacky when I don't know. Okay, but that's the wrong graph. Let me just do it again. Okay. So, oops. Let me add a graph. Okay. So this times cosine 2 times pi times x. The phase. Okay. Make sure everything is correct. Okay, I punch it in. Let me just zoom fit. Yeah, okay. So this is what I wanted. Okay. So let's do the second one. So Vs we have 100 cosine 2 pi is the radian frequency multiplied by x, which is time. And you multiply this in. Okay. Let me also zoom fit. Zoom fit. Ah, yes. Okay. So what you do is you put this in your calculator, you plot it out, and I recommend just getting like 1 or 2 periods of the graph. Okay, you don't have to scribble it like like this. You make sure you pull out your scale, your horizontal axis scale, so that the each waveform is clearer, and then you just extract like 1 or 2 periods from time equals to 0. Okay, there's no such thing as negative time, so don't take this side. Just take from 0 onwards. Just take 1 or 2 periods, and then that should be your answer. Okay, so this is for the last question of question 3. Okay, so let's move on to question 4. This is question 4. Wait. Okay. So question 4. Find V plus. Okay, so V plus. So of course, op amp. It is a no-brainer. So whenever we see the little triangle that is the op amp, immediately V plus equal to V minus, I plus equal to I minus, and then this is equal to 0 and KCL wherever possible. So find V plus. So let's just find V plus. So where's V plus? It's over here, right? So that means we just take a KCL at V plus immediately. So first we need to assume current direction. So let's say this is going in, then this is going out. So KCL at the plus terminal means current going in. So we need to express currents as V start minus Vn divided by R. So V start is here, starts at V2, ends at V plus, divided by R2. So starts at V2, ends at V plus, divided by R2, equals to, okay, what about the current leaving? So current going in is equal to current going out. The one going out starts at V plus, ends at ground. So V plus minus ground. V plus minus ground, which is 0, divided by R3. Okay, so our objective is to make V plus the subject. So I'm going to multiply R3 to this side. We get R3 V2 minus R3 V plus equals to multiply R2 to this side, R2 V plus. Then move V plus to this side. Yeah, move all the V plus term to one side. We get R2 V plus plus R3 V plus. Okay. And R3 V2 will be left here. Then you can see you can factorize out V plus here. Then you move this to the other side. In the end, you should get V plus is equal to R3 over R2 plus R3 divided by multiplied by V2, right? Let me check my answer. Yes, this is the answer. Okay. In your answer book, provide an operative definition or just describe what you are supposed to do. Okay, so what this means is virtual short circuit, and we've covered this in Devlin, okay? So go back to Devlin if you haven't remembered. Anyways, what it means to apply a virtual short circuit means to replace the device with a wire. Usually we do this for, what is it? We do this for voltage sources when we want to remove their effect, right? We do this to voltage sources, and we also do it to we do it to inductors. Yeah, so inductors at steady state are replaced with virtual short circuits. Okay, so that's what I mean by virtual short circuit. Just replace it with a wire. Okay, next we have this. So under the AC steady state condition, with a generic radiant frequency, determine the complex impedance for the resistors and the capacitors. Okay, so both R1 and R2 are the same value, which is 10 kilo ohms. R3 is 10 mega ohms. R4 is 10 mega ohms. R5 is 1 mega ohm. And ZC1 is 1 over J omega C. Wait. Yeah, ZC1 is 1 over J omega C1, which is 1 over J omega 0.1 microfarads. You don't have to punch this in. You don't have to evaluate it. Just leave it as it is. And then ZC3. What is ZC3? is, okay, so same thing, 1 over j omega c, omega, just keep it like that. C is 0.47 times 10 to the power negative 6. Just leave it like that. Is it just me or I can't find a ZC2 here? I don't know. Y'all tell me. I really can't find a ZC2, and I don't know why they put a ZC3. Anyways, yeah, so these are all the resistors and capacitors that I can find in the circuit. So now express the voltage as a function of V1 and V2. So put it simply, this means express V out in terms of V1 and V2. So let us go ahead and try to do that. Okay. So remember from op amps, we know V plus equal to V minus. We will use this fact later, okay? So let us now, okay, we've already taken a KCL at the plus terminal, right? Now let us take a KCL at the negative terminal. So assume the current directions. Going in like this, and then going out like this, see? Okay, so let me emphasize, this current will split like this, and then recombine here, right? So you can treat this entire thing, okay, treat this entire thing as a single impedance as ZA, okay? We will come back to that later. So now let us do a KCL at V minus. So who is the currents going in? Currents going in is this, which is V1, right? It starts at here, ends at here. So V1 minus V minus divided by R1. V1 minus V minus divided by R1. Now we move on to the current going out. So the current going out, see, it starts at V minus, it ends at V out. Okay, it ends at V out. So V minus minus V out. So V minus minus V out divided by ZA, because it passes through this lumped up impedance, right? This is C1 and R4, I lump it up as ZA. So it passes through ZA, that's why I divided by ZA. Okay, so now let us try to, what are we supposed to do? We are supposed to make V minus the subject. Now, why do we make V minus the subject? So that we can use this fact later and then equate it to V plus, right? We're making V minus the subject so that we can equate it to V plus later. So let us go ahead and do that. So cross multiply, you get this. Okay, move all the V minus term to one side. Right? This and this, I group it together and I factorize out the coefficients. Then this, I bring it over here. Okay, make V minus the subject, we have okay. Okay, so finally we got the expression for V minus. Now we use this fact, V plus equal to V minus, and then equate this to the V plus that we got from earlier. Where is that V plus? See, remember in the very first question, they asked us to determine V plus. So we are going to equate this with our V minus. So let us go ahead and do that. So let us start with V plus is equal to V minus. So let me check my working. Okay, let's just do it the other way around first because that's how I did it. V minus equal to V plus. So V minus is this, what we got earlier. Okay. Our objective here is to make V out the subject, right? Because remember, the question asks us express V out in terms of V1 and V2. So let us go ahead and do that. So how do I do it? I shall, let me see. make V out the subject. Okay. Let me just multiply this to this side, okay? Now we want to make V out the subject, right? So move this over here and move this over here. What shall you obtain? You shall obtain R1 V out equals to R3 R1 plus. Okay, then divide everything by R1 to get rid of this. So divide by R1, divided by R1, divide by R1. Then we finally get this. So okay, we're actually not done yet, right? Because remember, ZA is something that we arbitrarily created, right? ZA is the lumped up impedance of the capacitor and the inductor here in the feedback loop. So what do? We need to find ZA. So let us go ahead and find ZA. Because these two are parallel, let us use the parallel formula. So 1 over ZA is equal to 1 over J, 1 over ZC1, which we found earlier, plus 1 over R4. Okay? So actually, ZC1 is given by 1 over J omega C1. And then you make ZA the subject, you shall get 1 over R4 plus J omega C1. Now, if you want to beautify it by getting rid of uh, this fraction inside, you can multiply the top and the bottom by R4. So what you get is ZA equals to R4 over 1 plus J omega C1 R4. Okay, so that's ZA. Now what do? We need to substitute this into V out. So substitute this into here and here. Okay, a bit of a tedious job, but don't worry, it's actually pretty simple. Okay, so if you substitute that sub ZA, you'll finally get this. So it's pretty ugly, but it's okay. Just leave it as it is. Your examiner will understand this. And this. Okay, so this is your answer. I know it's a bit humongous, but it is what it is. Okay, so now in D part 2, assuming that V2 is 0 volts based on the previous calculations, plot the amplitude V out over V in. So I found this question quite funny in D part 1. So plot the amplitude means the Bode plot, the Bode plot, the Bode plot. But the thing is, to draw the Bode plot, right, you need the cutoff frequency, the maximum gain. But they will only ask you for the cutoff frequency only in part 2. And you also need the shape of the Bode plot, which is whether it's a low pass or high pass filter, which again is only asked in part 2. So let us do question D in a non-sequential manner. Okay, I don't know why they asked it that way, but it is what it is. So first, let us copy out our function of V out. Okay, what did they tell us? They told us V2 is now 0, right? So this is 0, means that we can switch this whole thing off. So this whole thing goes away. This whole thing cancels to 0, leaving behind this. So now our new V out is this. Okay, we want to find V out over V1, right? So move this to the other side. We get this. Okay. Okay. Determine whether it's a low pass or high pass filter. So to do so, you must take the limit, the low pass limit, I mean the low frequency limit of this expression. Okay. More specifically, right, you can just take the modulus. You see this negative sign outside? You can get rid of it by taking the modulus. Why? Why did we arbitrarily do that? It's actually not arbitrary. We are only interested in the magnitude of the gain. This negative only tells us that that our input is being inverted. You know, the negative value turn to positive value turn to negative value. It only tells us it's being inverted, but it's not telling us how much it's scaled. What we're interested is the scaling. So just take the magnitude of this, so we can get rid of the negative sign. Now we take the limit. So this goes to 0, meaning we only have R4 divided by R1. Now take the high frequency limit. Okay, magnitude is, get rid of this. This goes to infinity. See, 1 plus infinity is just infinity. Something times infinity will just also be infinity. So all of this goes to infinity. Then something divided by infinity will just be 0. Okay, now check the results. At low frequencies, you have something. At high frequencies, you have nothing. So what is this? This is a low pass filter. Okay, so we know it's a low pass filter. Find its cutoff frequency. So cutoff frequency, remember, you need to solve magnitude of the gain equals to the max gain divided by √2. Now, who is the max gain? Max gain is given by the non-zero limit. So see, this limit is 0, whereas R4 divided by R1 is the non-zero limit. So you take this is your H naught, and you sub it in. So what is our H? Our H is this, right? So copy this, paste. So we take the magnitude of this, is equals to, now our non-zero limit is R4 divided by R1 divided by √2. Okay, now let us simplify the left-hand side. Modulus means I can get rid of this negative sign. And then remember, this is equal to this. So essentially, I can split the modulus. So this modulus, split it. Then modulus of R4 is just R4 because resistance is positive. And then now try to make the numerators equal. So does this look like this? No. This is R4, but this is R4 divided by R1. So to make them the same, divide this by R1. So divide the top and bottom by R1. So divide this by R1 and divide the denominator by R1 also. So as you can see, R1 and R1 can cancel. You have R4 over R1 at the top. And then magnitude of this at the bottom. So you see, now that the numerators are equal, they can cancel, and then you can equate the denominators. So magnitude of a complex number is given by a squared plus b squared, square root of a squared plus b squared. Okay, next you can drop the square roots, and then 2 minus 1 is just 1. Okay, then you can square root both sides, and then rearrange to make omega alone. You shall get Wait. Sorry. This is R4. R4. And then this is R4. Sorry. Okay, so this is your cutoff frequency. So now you sub in the values. So 10 mega ohms multiplied by 0.1 microfarads. You should get 1 radian per second. And then if for some reason you're a demon, you want to change this to hertz, omega is equal to 2 pi f, which is, equal to 1. Then you make f the subject, you should get 1 over 2 pi. This is hertz. Okay? Okay. Okay, that's the... Okay, so we... Okay. So now we can sketch the Bode plot. So to sketch the Bode plot, number one, you need a shape, okay? The shape is asking whether it's a low pass or high pass. So we know that it's a low pass, right? We know that it's a low pass filter, so it should look something like this. Something at low frequencies, nothing at high frequencies. Okay, so now we need the max gain. So the max gain we know is R4 divided by R1, right? Remember? R4 divided by R1, this is our max gain. Okay, this is our max gain. If you sub in the numbers, 10 mega ohms divided by 10 kilo ohms, you should get 10 to the power 3. Okay? But remember, this scale is in decibels. And how to get decibels? Decibels, you need to take 20 log base 10 of the H value that you get. So we need to convert this to decibels. 20 log this, okay? This goes into here. So this, you can punch this in your calculator, but honestly, it's so easy you don't even need your calculator. Why? Just bring this down because laws of logarithm. So 3 times 20 log 10 base 10. And then you know that log a to the base a, this is just 1. So you know that this is 60 decibels. So the highest gain that you can achieve is 60 decibels. Over here, 60 dB. Now, let us label the cutoff frequency. So remember how to label the cutoff frequency? Start from the max gain. Drop by 3 decibels. So this is 57 dB. Draw a horizontal line across, cut through the graph, now drop down. This corresponding frequency is your cutoff frequency, which happens to be 1 radians. Let's just keep it in radians. So omega equals to 1 radian per second. And this is your Bode plot. Okay? Yeah. So actually this before part 1 is the answer for part 2. Yeah, I'm not sure why they rearrange it. They arrange this question in this order. It's kind of funny. But yeah. So that's 22, 23, Sem 1 in a nutshell.